In this part, I will solve the problem 2 of the sample final exam. Okay, so part 2 last year happened to be a design problem. So we need to design an isolated DC-DC converter. It has two outputs, dual output. The input between 100 to 200 volts DC, and first output is at 10 volts. Second output is much higher, 400 volts, and the maximum load currents for each of those output voltages are given, and specifications on the peak-to-peak ripple in the two output voltages. So note that the delta IL, the inductor current ripple, are not given, so you are free to choose your suitable value. And as always, the frequency is for the designer to select the appropriate frequency, so that also any suitable value can be chosen. There is also another requirement that the peak voltage rating of the MOSFET should not exceed 300 volts. And then similar to the homework and previous exam problems, the relationship between the ESR and the capacitance and the RMS current rating and the capacitance are given. Okay, so we need to give all the details needed to select the L and C final choice, and also the turns ratio and RMS current of primary and secondary windings for the transformer. And we are given that the magnetizing current can be assumed to be 5% of the peak of the load current component on the primary. Okay, so given these values, so you can see that the power level is relatively high. The first output is 10 volts at maximum current of 100 amperes, so that gives you the power in the first output to be 1 kilowatt, and you also have power in the second output as 400 volts times 1 ampere, so another 400 watts, so total of 1.4 kilowatt converter. So a good choice for that would be your full bridge converter. If you go back and look at the requirement on the peak voltage rating, it's 300 volts, which is less than twice the Vin max. So a forward converter with reset to primary turns ratio 1:1 will not be suitable, because that will result in 2 times Vin max as the voltage rating. That will be 400 volts, that would exceed this requirement. Similarly, flyback will also be Vin max plus the reflected voltage, the VO over N. So likely that term will also exceed the total of 400 volts. So from all of these considerations, your full bridge is a suitable choice. You can design a forward converter, but you have to make sure that the primary to reset turns ratio is appropriately chosen, so that V switch is at the maximum point, it is 300 volts or less. Okay, so I'm going to design for your full bridge isolated DC-DC. And once again, from the relatively higher power level, and also from the fact that in a full bridge converter, the filters see twice the switching frequency as the effective frequency, I will choose a frequency of 100 kilohertz. Okay. So a design with 200 kilohertz or 50 kilohertz is certainly acceptable, and so is your forward converter design, as long as I said earlier, it meets the switch voltage requirement. Flyback will rarely be used at kilowatt power level, so it's best not to consider a flyback for this application. So in any isolated converter, the first thing to design is the turns ratio of the transformer. So let's consider the output voltage 1, which is the 10 volts output. Right, so the turns ratio, we have an equation. I'll call this as N1 for the first output, and the equation in the notes is the output voltage VO1 divided by the D max times the Vin minimum. So VO1, no problem, it's given, it's 10 volts. So what is D max? In a full bridge, we can go theoretically as high as 1. So we'll just put that as D max is 1. We are considering ideal components times V in minimum is 100 volts. So N1 comes out to be just 0.1 turns ratio. Okay. So N secondary 1 divided by N primary is 0.1. Okay, so D max is 1 and D minimum can be calculated now once we have the turns ratio selected, or even by looking at this range. Vn change between 100 to 200, and if it is D max of 1 at 100 at 200 volts, it's going to be 1/2 of that. But we can use the formula that is given in the notes. So that would be the output required, 10 volts, divided by the turns ratio 0.1 times the D minimum, so it happens at the Vn max, which is 200 volts. Okay. So 10/20, that's 0.5. Okay, so that's the transformer turns ratio. I will come back and design the winding RMS currents later after we are done with the L and C for the first output. L1 for the output 1 filter inductance. The formula is VO1 minus DTS. For a full bridge, the frequency is effectively doubled. So we use 1 minus the minimum TS over 2 divided by the delta IL1. So we'll also make a choice for delta IL1 to be 10% of the IO1 max. Okay. So that's 0.1 times IO1 max of 100 amperes. That'd be 10. So substituting those is 10 volts output, 1 minus D minimum of 0.5. TS, 100 kilohertz TS would be 10 microsecond. So TS over 2 would be 5 microseconds divided by delta IL1 required was 10 amperes. So that gives me L1 to be 2.5 microhenry. Okay. Then the other parameters needed, IL1 peak would be the average current is 100 amperes at the maximum load current is 100 plus the peak to peak ripple is 10, so 10 over 2 or 105 amperes is the peak. We can approximate the IL1 RMS is as the IL1 DC bias to be 100 amperes maximum load current. Okay, those are the parameters needed to physically design the inductance. So that will complete the inductor design for output 1. For capacitor, we need to consider several things. We need to find the ESR required, the ESR limit, the RMS current rating, and so on. So we'll start, maybe we'll go to the next slide. Okay, we are still in the output 1 and the capacitor. Okay, so the ESR limit less than or equal to the delta VO1 allowed divided by delta IL1 that we chose. So delta VO1 is 50 millivolts divided by delta IL1 we allowed 10 amperes. So that will be 5 milliohms or 5 10 to the minus 3 milliohms. That's one requirement, and if you based on this, the C value needed, okay, if you substitute this 5 milliohm in this expression, right? If you say ESR is 5 milliohms, so you have 5 10 to the minus 3 is 100 10 to the minus 6 over C, so you can calculate C. Okay, so from ESR requirement, the C comes out to be quite a large values, 20 millifarad. The reason why it is so big is a fairly stringent requirement on the delta VO, just 50 millivolts, and the fact that the current is really high, 100 amperes current. So anyway, so this is probably going to be the dominating requirement. but we can go ahead and calculate the IC RMS rating. This we have a formula which is the delta IL1 chosen divided by 2 square root 3. So delta IL1 was 10, 10 over 2 square root 3 is 2.886, and this requires a C from the second relation here, it's 5000 times C, or C needed would be IC RMS divided by 5000. Okay, so that's 2.886 divided by 5000 gives me 577.2 microfarad. Okay. So we would use this value, right? Choose this because that is the highest requirement, that is the worst case requirement. Okay, the V rating, this is VO1, so 10 volts, you can say plus margin. Okay, you may also go ahead and calculate the C needed based on ideal capacitor assumption, and it will come out to be much less than 1/10 or 1/100th of this value. So, so this would be our final capacitor chosen. Okay, so then moving on to output 2. Okay, so again the turns ratio for that, call that as N2. You can use the same formula that we used to calculate N1 with the new or the second output voltage, or simpler would be to use the formula that the N1 over N2 would be VO1 over VO2. So that is 10 over 400. Okay. Makes N2 to be N1 was 0.1 times 400 over 10. Okay. So that's 40 times 0.1 is 4. The turns ratio is 4. So it's a step up winding with a step up ratio of 4. Okay. The Dmax and Dmin are common for all the windings, all the voltages. So Dmax is 1 and D minimum is 0.5. Okay. There's only one control freedom, which is the D of just one duty ratio for the entire converter. It does not change with multiple outputs. Okay, then inductor L2 for the second output. Same formula, VO times 1 minus D minimum, which is 0.5. TS over 2 is 5 micro, and delta IL2, sorry. Okay. So I will choose delta IL2 also to be 10% of the IO2 max, which is 1 ampere. So this is going to be 0.1 ampere. So that gives me an L2 required of 10 millihenry. Again, fairly large L value, but because the current is very small, just 1 ampere, it still be a relatively small inductance. Okay, the IL peak, IL2 peak would be the average of 1 plus 0.1 over 2, 1.05, and IL RMS, IL2 DC is 1 ampere. Okay, selecting C2, the capacitor for the second output voltage. So ESR limit would be delta VO for the second output is 2 volts. So it's 2 volts divided by delta IL2 of 0.1 ampere. It's a big ESR value. So we can use a really small capacitance in this case. So this will, again, using the similar method as we did for the first winding, first output voltage, C2 required for this much ESR is 5 microfarad, very small capacitance, and the IC2 RMS would be delta IL2 over 2 square root 3, so 0.1 over 2 square root 3, so that's a very small value, 0.029 amperes, and this would require your capacitance. Actually, this is slightly different, 5.77 microfarad. Okay, so basically IC RMS divided by 5000 gives you 5.77 microfarad. And now the reason why I said it's slightly different is unlike the first output voltage, now the dominating requirement for the capacitor C2 is the RMS current rating. So we use choose this capacitance for C2. Okay, V rating is high, same as VO2, which is 400 volts plus margin. Okay, so that completes the L and C design for the 2 windings. Then we need to look at the transformer RMS currents. We already have the turns ratios, transformer RMS current ratings. So recall that the Dmax is 1. So for secondary, again secondary 1, first output voltage, IRMS secondary 1. So that will be, it conducts 100 amperes whenever it conducts, and it conducts with a Dmax of 1. But on the secondary side, for the center tapped arrangement, so we will need to draw the schematic anyway. So let me go ahead and draw the schematic here. So it's a full bridge, 4 switches. Okay. It's okay if we just draw the ideal switch symbol, does not have to be MOSFET symbol. The DC input voltage 100 to 200 volts, and this gets connected to a primary. Then there are really 2 secondaries, and both of them center tapped. Okay, let's call this as output 1. Right, so that's the first output, BO1. Okay, we can write the L values and C values that we calculated. The dots would be as shown here. Okay, but this is just one secondary, or one set of secondary windings. So the second output voltage will have another set of center tapped windings. So VO2, and the L and C values we calculated. Once again, the dots are like this, and just to indicate that they're all on the same core, you can just put something like that. They indicate that all these windings belong to the same core. So given this center tapped arrangement, the secondary current would be given by the full inductor current whenever it conducts, and the ratio of the time for which it conducts in one switching period. So that would be 0.5, so square root of 0.5. So that's 70.71 amperes. That would be the RMS current in both of these 2 secondary windings corresponding to the first output. Similarly for secondary 2, so IRMS secondary 2 would be its own inductor current, which is maximum of 1 ampere times the same square root of 0.5. So it's 0.7. Okay, then primary is slightly more involved. So I RMS, there's one primary. Okay, so that now the primary current, unlike the secondary, which if you look at this current here, it's only when this diode conducts, whereas the primary current is positive and negative, and something like that. That would be the primary current. Okay. And to that we will also, when we draw the actual waveform, we'll also draw the magnetizing current, but it does not contribute much to the RMS value, so we can just consider this as a square wave current. Okay. So IRMS primary has contributions from two both these output voltages and their respective currents. So the turns ratio for when you consider the first output voltage, it's 100 amperes on the secondary times the turns ratio, which we calculated was 0.1. Okay. But that's not the complete load current component. There is also a load current component on the primary due to the second output. So that would be the second, this secondary current here, which was 1 ampere maximum, but the turns ratio is 4. Okay, so that's 10 plus 4, 14 amperes. That is the RMS current in the primary. Okay. The last one is the switches current voltage ratings. For the MOSFETs, V rating is same as the maximum input voltage, which is 200 volts, and peak current rating would be, now just consider the ripple as well. So the peak current for the inductor with the ripple considered, the peak to peak ripple was 10 amperes, so the total current was 100 plus 10 over 2 times the N1, which is 0.1, plus the second one had 1.05 as the peak times 4. Okay. So this is 15.435. I'm sorry. Well, this is just the load current component peak value, and it is given in the problem statement that there is a magnetizing current not to be neglected. It is to be assumed as 5% of this value of the reflected load current component. So this times 5% times 1.05, that is what is the 15.435. So that will be the peak current rating for all the 4 switches, and the voltage rating is 200 volts again for all the switches, and again clearly mention that satisfies the 300 volts limit. Okay. Remember that one of the requirement was that the MOSFET should not have a requirement of more than 300 volts rating. Okay, for diodes, output 1, its V rating is 2 times N1, because when a diode is blocking a voltage, it sees both the secondary windings of that particular output voltage. So it's 2 times N1 times the input voltage maximum, Bn max, which is 200. N1 is 0.1, so it comes out to be 40 volts. Current rating for the diodes is simply the 100 amperes times the 1 minus D minimum. Which is 50 amperes. Okay, or probably an easier way to say this is 100 amperes total current, and the diodes share the current equally, so that's 100 over 2 also is 50 amperes. Okay, either way is fine. And of course I peak is same as the MOSFET, so no, it's on the secondary side. So I peak, you can write it explicitly for the diode, is also 105 amperes. Okay. Output to very similar thing. V is 1600 volts. Okay, it's 2 times N2, so N2 is 4, so 8 times the V in max of 200 volts at 1600 volts. Current I peak is 1.05. We saw this earlier, but the I average is 0.5. It's again 1/2 of the maximum load current for each diode. Okay, so that together with the schematic which we already completed previously, that completes the problem. And when you give the turns ratio, okay, here, so you can specify. So this is 1, N1, N1, N2, N2, and then that together with your values for N1 and N2 as part of the problem, that will be a complete representation or the complete schematic.